In this lecture, we study about calculation of leakage reactance of a SCART connected transformer. Genesis. The SCART connection is one means of making the three-phase to two-phase transformation. So that is the main purpose. It utilizes two single-phase transformers, perfectly similar transformers connected to the three-phase system and to one another in such a way that the output replicates a balanced two-phase system. So the secondary side is a single phase, each phase will constitute of two-phase system. So the primary side, three-phase system is connected. We will see how that will be realized. It can also be used to reduce the extent of phase imbalance when single-phase loads are supplied from three-phase supplies. So when single-phase loads are supplied from three-phase supplies. So if we use SCART connection, then it reduces the extent of unbalance. So SCART connection is shown here typically. So this is three-phase system. So this is one transformer. Here this primary and this secondary. AS is primary and this teaser, its secondary is this. So this is one transformer. It is called a teaser transformer. And the other transformer is this one. So BC or CB is primary and this V1 is secondary. So the this is called main transformer. The main transformer should have 50% tap, and the teaser transformer should have 86.66% tap, that we will see soon. So this is how two transformers are connected, and then the output side means this red phases are two-phase system and input side is three-phase system. This is how it is achieved. Balanced two-phase system. In a balanced two-phase system, there are two circuits with two wires for each phase carrying alternating current of the same frequency and voltage magnitude, but with a phase difference of 1/4 of a cycle, means 90 degrees, 90 electrical degrees. So this is the system VA and VB. So VB is 90 degrees lagging, but the voltage magnitude is same. VA, magnitude of VA, magnitude of VB is equal to V only. So this is how the time domain voltages will look like. So the phase difference is 0 to 90 degrees. And then two-phase supply systems are used in applications such as heavy-duty welding machines, furnaces, etc. The SCART connection. What is SCART connection? So let ABC denote the terminals of a three-phase system. If three single-phase transformers are connected from forming a star connection, their primary windings may be represented by the lines AN, BN, CN, like this. So if the line AN is extended to the midpoint M of the BC, here BC, and midpoint M, then it is evident that AM is perpendicular to BC, and that it would be possible to form a three-phase bank using only two single-phase transformers. So their respective primary windings being represented in terms of phasors by the lines AM and BC respectively. So what will happen if we connect, this is a three-phase system. So if we connect some winding between C and B directly, so one single winding, and then take a tap in between exactly at the middle point. So what will happen? What will be the voltage at the midpoint? This is point C, this is point B, right? Point B. Now exactly at the midpoint, what will be the voltage will be exactly 50% of the voltage. So this winding is single winding. So we have to remember that this is single winding, and BC is like this. At the midpoint, you will get exactly 50% of the voltage. Now, if any symmetrical or anything is connected from any point to this midpoint. So this since that is symmetrical to both C and B, so it won't affect this distribution actually. So this will be BC voltage BC. So on this line to line voltage will be there on this phase itself. So that's how this transformer primary, BC transformer, main transformer primary will be there. And here what will be done is AN, whatever you connect here again, the potential will be exactly like AM only. So which is perpendicular to BC. So this is how the phasor diagram will be there. And there is a SCOT connection contained. Thus a SCOT connection utilizes two single phase transformers connected to the three phase supply with a ratio of primary winding turns equal to the ratio AM by BC. See, the primary windings ratio should be in this rate. Why it is required? Because two similar transformers, if you connect them, see, if you connect one transformer like this and to the midpoint another transformer like this, okay, and then the voltage here in this phase will be exactly perpendicular to the voltage here, right? So like this. But what will happen, you are using, this is the secondary of this transformer and this is the secondary of this transformer. So unless voltage per turn is constant, you will not have same voltage at the secondary. Magnitude phase anyway is achieved by this simple connection, that midpoint connection itself. So if you connect BC, the primary winding, and take a midpoint tap and connect the third one, and then connect these two phase A, then this voltage will be 90 degrees away from this voltage. So therefore this is achieved already. Even if you put different number of turns between A and this M, midpoint M, AM, then also AM will be perpendicular to BC only. But why should we keep only 86.6% of the turns here? There is a reason, because voltage per turn should be constant in this transformer as well as in this transformer. Then only you will get, since same number of turns are expected to be used here, so then only you will get same amount of voltage V here, V here, V2 you can say, V2. So otherwise it is not possible. That is why, so the tap for the first transformer is to be at 9, so the teaser transformer is to be at 86.6%, and the tap for the main transformer is to be at 50% of the winding, of primary winding. So both are primary winding taps only. So the secondary winding you can see is full actually, here also full. So this is, if equal number of turns are there, it is expected, because both transformers are same, assuming same. So N1 equals to N2. Then since voltage per turn is constant here, so in a given transformer, voltage per turn is constant. Please remember, voltage per turn, irrespective of secondary, primary, whatever it is. So voltage per turn is constant. Therefore, if you use same number of turns in the secondary, then always you will get same voltage magnitude, and the phase is already 90 degrees away from each other. So this is how the SCOT connection achieves 3-phase to 3-phase 2-phase transformation. If if the line AN is extended, yes, we have seen this. Now, thus the SCOT connection utilizes two single-phase transformer connected to a 3-phase supply with the ratio of primary winding turns equal to the ratio of AM by BC. The secondary windings of each of these transformers has the same number of turns, such that the output voltage magnitude is the same. Therefore, the output tapped from the secondary winding of these two single phase transformers forms a balanced two-phase system. The transformer with the primary having a larger number of turns equivalent to BC is called the main transformer, and it has primary winding center tapped, 50% tapped, and the connection brought out for the connection to one primary pole of the other transformer called teaser transformer. The other transformer is called teaser transformer. Actually, it also should have 86.6 percentage tap. So there only you have to connect this one, so that the voltage per turns remains constant. Of course, if voltage per turn does not remain constant, is it possible to obtain a Scott connection? You should have different number of turns in the secondary, then only it is possible. Yeah, that you have to remember. Now we have, see here the connections are, transformers are given individually. This is one transformer, main transformer, and this is the teaser transformer as shown here. Now for main transformer is connected between B and C, and then here the complete winding is given here, and then at the midpoint it is tapped, and then the teaser transformer is connected here. So this is the teaser transformer primary, and then this is the secondary of the teaser transformer. Now this is the secondary of the main transformer, and here V2 is V angle 0 and V angle 90 here is V1. So thus we have NPT divided by NPM. NPT, number of turns on primary transformer, primary side of teaser transformer, NPT divided by NPM. NPM is the total winding of the primary side of the main transformer. NPT by NPM is equal to AM by BC. AM by BC in this figure, AM by BC equals to root 3 by 2 into L by L is equal to root 3 by 2. That's what is the ratio between this and this. So the primary of teaser transformer is just root 3 by 2 of the primary of the main transformer, number of turns. So what does it mean? Root 3 by 2, 1.732 by 2 is 0.8 6 like this. So 0.866 or 86.6 percentage of the turns of the main transformer will only be having on the teaser transformer. So if you have exactly similar transformers, what you have to do? You have to tap at 86.6 percentage and then connect the main winding. Primary winding of the teaser transformer. Then what will happen? Automatically voltage per turn will remain same, and at the secondary side you will get exactly the magnitude of voltage will remain same. Otherwise what will happen? If you connect, suppose here also full winding, then the voltage per turn in this will be different. So accordingly you have to increase the number of turns on the secondary side, so that the ratio will if you include full number of turns, what will happen? The voltage will remain same. So but voltage, the number of turns, if you take exactly same number of turns as before, you will be getting for example here AM, the voltage is 0.866 times the voltage V line or VBC. So this much only voltage you will be getting at the primary side of this transformer. Accordingly you will get 0.866 times of V2 only you will be getting here in this V1. So you will not get full voltage, because the voltage per turn gets reduced because if you use more number of turns. So therefore you have to increase the number of turns on N2, then only it will happen. You can get equal voltage if you do not use tapping on the primary side. Therefore tapping is a must 0.866 percentage tap you have to use. Otherwise, you have to use different turns ratio. So if you have similar transformers, if the turns ratio is same, then obviously you have to use 0.866 or 86.6 percentage tap at the primary side, so that you will have same voltage per turn and then same output voltage as that of the main transformer. So this is how SCOT connection has to be done. So here NST, N secondary side of teaser transformer, is same as N secondary side of main transformer, equals to N2, say, let us say. Thus, if VL is the three-phase line-to-line voltage, then the voltage across the primary of the main is VL, but voltage across the primary of teaser is this much only, root 3 by 2 VL only. This, remember, this will not change with respect to the turns, number of turns of primary. You can you connect irrespective of any connection here, any number of turns, you will always get root 3 by 2 voltage only. Since root 3 by 2 VL you are getting, you have to make the number of turns also root 3 by 2 times of that main transformer, so that voltage per turn will remain same, and the secondary side you will get the same voltage. Thus NPT into IA equals to root 3 by 2 into NPM into IA, or equals to N2I2 equal to N2I1, since I1 is equal to I2. So this you remember, NPT into IA, that is NPT into IA, because IA is the current through this winding. So NPT is the number of turns, NPT into IA is the ampere turns or MMF produced by this winding, which must be equal and opposite to that produced by the secondary. Therefore, N2 into I1. Since I1 is equal to I2, this must be equal to N2 I2 also. Therefore, that must be equals to then I1 must be equals to I2. Therefore, when doing the calculations for the leakage reactance, what is to be done? For three-phase side, three-phase current you should have. So IA you should have. So this equation you should use, three-phase side. So root 3 by 2 into NPM into IA is the three-phase side magnetomotive force. And for two-phase side, the MMF is N2 I2 or equals to N2 I2 equals to N2 I1, which is also equals to root 3 by 2 NPM into IA, MMF three-phase side. Both are same actually, but when calculation you have to use so that the terms cancel out. IA in calculation of leakage reactance, you again do not expect the value IA there. Only it should be in geometrical number of turns and geometrical size of the transformer. Therefore, the IA should cancel out. That's how we will use the formula, and I will show just in the next slide. So this is the current IC here, how the three-phase currents will get actually. There will be an IB dash current induced in the primary winding of the main transformer due to the flow of load current I2. So this IB dash flows in the main winding of the primary winding of the main transformer. So IB dash will be like this. In the phasor of IB dash will be like this. IB dash will be adding with IA by 2 minus IA by 2 and then making this IB. So this is minus IA by 2 and here also minus IA by 2. So minus IB dash and then minus IA by 2 will be making IC. So this how IB and IC phasors will be there. So the balanced three-phase current IB, IA, IB and IC will flow through the terminals of the three-phase system. But internally what will happen? The current IB dash will be induced in the primary winding of the primary winding of the main transformer, due to the flow of load current I2. So, however, due to the center tapping of the direction of the induced currents in both halves of the primary winding is opposite, thus cancelling out the each other's effect. If the turns ratio of the primaries of the teaser and main transformer is not equal to root 3 by 2, the voltage across the secondaries of the transformer will not be same. That's what I have just now discussed. So therefore the turns ratio of the primaries should be in this order. One is 86.6%. The teaser transformer should have 86.6% of the turns of the primary winding with respect to the main transformer. So this is how the Scott connection is made possible. Now the calculation of leakage reactance. So that for that we need energy stored in the transformer. Since we have two transformers in Scott connection, one transformer you consider here maybe, so you may consider that both of them are equal height, the windings are equal height, and there is an air gap like this. So if primary and secondary are of equal height and total primary ampere turns are again same, MMF is same, the MMF wave will be trapezoidal as shown here. It is increasing, and then in the air gap it will remain constant and then go down like this. Now total MMF is known, so this formula is similar to whatever we have done. For main transformer there is no issue because both this winding is 100% in use, and then this secondary winding is also 100% in use. So there will be no issue, the MMF will be exactly same like this. So thus the total energy stored in the entire system by virtue of leakage flux is in the main transformer alone, is E1 plus E2 plus EG, means E1 is energy stored in the primary, E2 is energy stored in the secondary, EG is in the gap. So which is given by half mu naught MMF square divided by HR pi into D1 plus W1 by 3, the width by 3, D2 into W2 by 3 plus DG into WG. D1, D2, DG are mean diameters of these things. So here you can see the MMF. What is to be used for MMF? MMF, if you are considering three-phase system, then three-phase side MMF you have to use, and then if you are considering three-phase side current should come in the MMF equation. So that's how you have to do. And then if it is two-phase system, two-phase side current should come. So I will just show that one. Then let us go to teaser transformer. Teaser transformer, actually there will be radial energy. For example, if the windings are of this height and same height, sorry, not here. So I will just use eraser and then yeah. Now let us see this. This is the primary winding of the teaser transformer. Okay, and this is the secondary winding of the teaser transformer. Now, if you were to use 86.6% tap, then obviously this only the winding of this much height will only be used. This winding is not used. So in this case, of course, this is the axial MMF. This will be there. But in this case, radial MMF will also be there here. So here, since there is no winding, this is you may consider this as negative or positive, whatever you want. So then this may increase to some extent up to this. Increase to some extent, and then it will become 0 like this. So this is how the MMF wave will be there in the radial direction also. But ignoring such an effect, suppose you have a separate transformer with 86.66% turns on the primary, and the secondary turns are same as the secondary of main transformer. So such a teaser transformer if you have, then this calculation will hold. Otherwise, you have to consider this radial MMF also, and then include in the total the energy, corresponding energy you have to include in the total energy calculation. So if you neglect this radial energy, or you consider the transformer which you have with 86.6% of primary turns and the same number of secondary turns, then the energy stored in that transformer also will be given by this equation. Then for the same type of transformers neglecting radial energy, on the three-phase side, the per phase total inductance L. Per phase total inductance means L1 plus L2 dash. L1 plus L2 dash. That is per phase, total inductance. That means, secondary side leakage reactance is referred to the primary. That's what it is. So if this is L, then it is the equation is 3 into half L Ia square, because three-phase system, three phases you have. So L is per phase only. So half into L into Ia square. Ia means Ia equals to Ib is equal to Ic. So Ia square means that is the total energy on the primary side, equals to, here MMF I have replaced with root 3 by 2 NPM into Ia, because this Ia should get cancelled out with this Ia here and here. So that is the purpose. You have to use this equation. So this is how. Then simplifying this, you will get what is the value of L. That is the inductance, per phase total inductance referred to three-phase side. And if you want for two-phase side, per phase total leakage inductance L is given by, for two-phase side, 2 times of Li2 square. See, the total energy in the transformer is also doubled here in this equation also. Please see, go back and see here also 2 times. Means there are 2 transformers, right? Main and teaser transformer. That's why this 2 has come here. If they are dissimilar, then you have to use 2 different equations for them. But since we have considered them to be similar and neglected radial energy in teaser transformer, so that's how this 2 times the term has come here. And since two-phase system, only 2 phases are there, again this here it is 2 times half Li2 square. Unlike in this case where the 3-phase system, there are 3 phases, 3 times half Li square. So this, if you simplify, you will get L again. In this case, L is total inductance, total per phase inductance referred to two-phase side. So this is how the calculations of leakage reactance can be done for SCOT connection. And as a assignment, you may solve it considering radial energy as an assignment. That's what in the previous slide I have shown. So include the radial energy also, and then find it out the total leakage reactance referred to primary, referred to three-phase side as well as two-phase side. So this as a homework. So this is how the leakage reactance can be calculated for SCOT connection. Thank you.